Uh, when I asked Rosemary for have some time to give a talk, I asked her for 15 minutes, and then she offers me 45 minutes, and you clearly see that 25 or 24 transparencies in 15 minutes is not possible. And the reason is because I extended the title. I don't want to speak alone about selection bias. I also will talk about chronological bias. And by offering me such a high amount of time, I can tell you the story, which I think is important, which is clearly related to what Bill and other are telling us before. So this is the outline of my talk. I will give you an introduction, then I will tell you something about the setting, which includes a model and some result. And then I will go to the assessment and we'll draw some conclusions. So mainly, and I will first go, yes, okay, I'm in the right order. I will go from the introduction. As you already know what I stated yesterday, there was a paper of Yopi in 2013 who stated that there are 63 orphan drug legislation in the European Commission in the time between 2000 and 2010. And the interesting fact from the randomization perspective is that 21 of these orphan drug legislations involve open-labeled trials. So clearly, when we have open-label trials, we think about selection bias. So bias may affect the results. But it is also so that you have these problems in double-blinded trials. I mean, one of the persons who give some discussion about that is Berger, who stated that if you have some information about the side effects, you can have some predictability about what is the better or the or drug A or drug B, and that introduces already selection bias. So you not need to know the block size in a block experiment. Well, and then there's a statement of the EMA guideline, ICH guideline, which is also the same thing, E9, where it stated that treatment comparison should involve consideration about the potential contribution of bias to the p-value and to the estimates and confidence interval. And I will deal with the p-value, okay? Because I think that is a very important point if you communicate with a physician. I mean, if you tell him something about guessing or something like that, I mean, I have a coworker of mine who did that frequently, and they all say, guessing? I don't know. What do you mean? I'll never guess. Clearly he does. Everybody of us does, but he will not accept that argument. And so we have to show them what is the influence on the test decision of our final test decision, and then therefore the p-value is an important number which he knows, because he wants to have a low p-value. And then I found I have done a lot of support and consultation in the formulation of clinical trial protocols, and I have read as many papers as Bill did in the applied scientists. So there's less or no recommendation about giving scientific arguments for the selection of a particular randomization procedure, and there's a clear lack, because I think that is very important, as you mentioned before, Bill. Well, and then we have a lot of, I think it's the right word, a lot of criteria, because it's plural. A lot of criteria which should be outweighed and should be given to the physician, and which are very important. And then I was aware of a framework which was presented by Bender in a 2010 paper, who recommended a so-called clinical scenario evaluation, where you put in some assumptions and then you evaluate your scenario, your design, and whatsoever, and then you see what happens, and by this you select the best thing. So, and that brings me to the objective of my talk. The purpose is to present a tool for assessing the impact of selection bias as well as chronological bias on the type 1 error probability for a given randomization sequence or randomization procedure. You will see the difference later on, and thus enabling a scientific discussion of an appropriate choice of a randomization procedure. So it's partly presenting a framework, and partly there are some scientific or some math behind that. So let's start with the setting. The setting is, I will start with a very simple model, which is a 2-arm parallel group design, and with a continuous endpoint normally distributed. I have a treatment effect under treatment A and B, mu A, mu B. Z is the allocation generator, or that's what is given from the randomization procedure. It will be 0 or 1 if the patient is allocated to treatment A and to treatment B. And tau I is for the moment a fixed unobserved bias effect acting on the response of treatment I. And the specificity of that model is that the numbering I is according to the sequence a patient is enrolled in the trial, and that makes it necessary to put the ZI here, but that facilitates much other things. So what I will do in the following is I aim to test the hypothesis mu R against mu B, and the null hypothesis is the effect is comparable in both groups versus the alternative hypothesis that the effect is different. And I use the wrong test. Because tau I is unobserved, I use the wrong test, the t-test. And that is the t-test formulation reflecting the fact that I use a ZI here, and the numbering is over all individuals, because ZI takes values 0 and 1. It brings you here the variance of the observations under treatment A and the variance of the observations under treatment B, and here the means and so on. And I write it again here, and that's why I put a tilde over there, so that you be aware that the writing is a little bit different, but it's a usual t-test anymore. So usually we will apply a t-test with the non-centrality parameter 0 to that situation and calculate the p-value. But we know that is a misspecification model, so that's wrong. So what is the true distribution of the t-statistic? Well, the true distribution is nowadays a doubly non-central t-distribution with NA plus NB minus 2 degrees of freedom. And it has 2 non-centrality parameters, not 1 non-centrality parameter. The first one is that one here, which is some kind of a location shift based on the bias which is given to the patient, the mean bias which is given to the patients receiving treatment A, and the mean bias given to the patients receiving treatment B. And here is some kind of pooled variation in that. So this is more a scaling parameter, and that is a location parameter for this distribution. There's not so many known about this distribution concerning I mean symmetry or something like that, but we will use it. Well, why is it like that? Well, every patient has another mean under the response, and so we do not have the mu A and mu B as a mean, and so that is the problem in the derivation of the distribution. I will give you some more details. What I stated just before is given in this statement here. If you calculate the distribution for the mean difference in the model, you have mu A minus mu B as an expectation, plus the shift based on the bias, and here is the variance given by that, and uniformly of that, it can be shown that the expression in the denominator of the t-test statistics has a chi-square distribution with this non-centrality parameter, which can be calculated over the variances, and that is all based on, or can all be found in the book of Johnson, Kotz, and Balakrishna, 1994, I think chapter 13 or something like that. Anyway, okay, under the assumption that mu A is equal to mu B, the first parameter, which is only affected by the null hypothesis, results in that expression, and the second parameter, non-centrality parameter, results in that expression. Well, and then there's a paper of Kocher-Lakota, 1991, where they make some evaluation of the double non-central T distribution, and they found this symmetry conditions, which mainly means that if you have minus the T here and minus the first non-centrality parameter, then it corresponds in this way to each other, so that I get this expression here. So what is it for? I mean, that's the theory. What is it for? Now I'm able to evaluate any randomization procedure, or more specific, any randomization sequence, and calculate the true p-value if I impute any kind of bias. So I need some formulation for the bias, okay? Am I in the right direction? No, that's wrong. I have to go that way. Bill, thanks again. I just briefly have to mention some of, only 4 of the huge number of procedures you just introduced. I will, roughly speaking, about complete randomization. Then I will mention random allocation rule, which is also one of the prominent randomization procedure applied in clinical trials, then permuted block randomization. And then I will talk about your winner and my favorite, big stick design. And well, let me add some comments to what you have said. Well, A is, in contrast to the Berger maximum procedure. In the Berger maximum procedure, it is usually the case that you have a terminal balance, which you don't have in the big stick design. You have imbalance over the whole range, and that makes it very nice. So how do I get to A? My recommendation is, I mean, if you have done a sample size calculation, you can see how you can relax the balance force. Because, I mean, everybody of you know that that sometimes imbalance is better than balance. For example, if you have a dichotomous test, if you have a chi-square test at the end, imbalance is better than balance, more powerful. And you can relax the balance in a t-test scenario very, very much, even if you have a large effect. So balance is not such a big problem for me. And if you say, okay, my aim is 80% power at the end, but I'm satisfied with 75% power. Okay, I mean, I have to notice that imbalance occurs in every clinical trial because of missing values and so on. So you must have a relaxing in that. If you can lower your power in that case, then controversially you can calculate the A, which is the relaxing factor. So that is my recommendation to come to an A. Okay, well, and then we come to the selection bias effect. Now I have to say something additional. I mean, guessing is a nice thing, but if I have a consultation with a doctor, I have 2 problems. First, he ignores that he will guess anything. And the second thing is another thing. If you have a clinical trial in a very homogeneous population, so no difference, say twins. So, yeah, I mean, you can guess as what you want, but you will not see an effect on the treatment effect estimate. And that sometimes happens in rare diseases where you have, for example, a family which is affected, and it can be assumed that the family is a very homogeneous population because no other will be affected. And similar results may hold if the population is so heterogeneous that you cannot identify a classification system. So what we do is we thought that there is some identification of the population, so that we can impose some eta for the modification of the treatment effect based on the bias on the convergence strategy which is introduced by Blackwood and Hall. Okay. So the terminology is as follows. This expression here is when is the selection bias policy, which we call selection bias policy, active. And Miriam Tam, a student worker of mine, number, I don't know number, 4, 5, something like that, she has introduced this general expression, which is more or less the number of already assigned, of remaining assignment to treatment A related to the number of remaining assignment to treatment A and B. And if you have this proportion in mind and you have a cutoff point Q, then you decide to pick up one person who has a better response or a worse response, and if it is between 1 minus Q and Q, it is a neutral patient. So the easiest thing is if Q is equal to 1.5, then you have NB, the number of previous assignment to B, should be greater to NA, and then you select somebody who's getting the A treatment. That can be formalized in this way, and this is our biasing policy. And now I show you that the worst case, as you clearly know, is the case Q equal to 1/2. I mean, everybody, if you understand that if Q equal to 1, no biasing is available. So we have this randomized clinical trial in twins, and only neutral patients are there. So that must be the neutral place. And the other case is Q equal to 1. We've done some simulation, and well, I have to specify a little bit more. The eta, the selection bias effect, is half of the effect which is detectable by a sample size of 40. I relaxed my 8. Okay, the sample size is 40. You calculate the true treatment effect, which is detectable, and then you take half of this as a selection bias effect, which might be very strong, but I will tell you something about choosing this later on. Then I perform a usual t-test. And here is permuted block randomization with block size 4 and block size 8 and block size 10. And clearly you see that if you relax the block size, the p-values are going down, so that you probably maintain the significance level. In the case Q equal to 1, you have only neutral patients, you maintain the 5% significance level. In every other case, no. And the worst case is Q equal to 1/2. And you see that longer block sizes prevent to selection bias if you look at the p-value. A well-known result, but anyway, I mean, that is better, I think, better to communicate in some sense. Okay, then I compare the procedures to each other and look to the p-value. I think you have done a similar for in one of your transparencies. So I look for complete randomization, random allocation rule, permuted block randomization, and here my winner. But I used big stick design of with relaxing factor 2, not my recommended part, but to make the results comparable. But because if you have a sample size of 8, yeah, then if you relax it much more, then you are leaving to complete randomization, and that there is no difference in that. Well, let's look to the again, the eta is chosen according to the rule which I already presented. You see that, well, this is more or less, I think, this is rounding errors from our simulation, because 100,000 should be too small. It should be 5% here in any case, I guess. Then you see that random allocation rule is better than permuted block randomization of size 4. If you have permuted block randomization and you increase the sample size, and parallel to that, the treatment, the effect size is decreased, which I could detect with a sample size of 40. But nevertheless, the influence on the permuted block randomization is given, and it is, I think it is very high. And also, my winner is big stick design. Yeah. So nothing new. Okay, so we found at that place for selection bias that the type 1 error increases with smaller block sizes and a permuted block randomization, that the type 1 error decreases with higher value of Q, and the elevation are substantial even if you have Q equal to 2/3. So a very small area where you can decide on better fitting patients to the treatment effects. And by the way, I have to say that we have done also some simulations where we have random eta included in the model, and they are similar with that. Okay, then the point with chronological bias, or what is sometimes called linear time trend. So there are a lot of arguments, and Bill has given these arguments to us for imputing some chronological effect or time trend effect in population where rare diseases are effective. One can think about changes in a population characteristic. One can also think about other things, like, I mean, most of the diseases could be treated also by surgery, and the surgeon has a learning curve, and there are some publications about learning curves, and these could also make the tau I in these things. Changes in diagnostic potential, and so on, whatever you need. And this is a special form, what Bill already mentioned, of accidental bias. Miriam has done in her publications, considered various forms of chronological bias by imputing a linear time trend in the data, by imputing a stepwise time trend in the data, which might be a worse thing to do if you have an adaptive design. Might be, I don't know. Log time trend for surgery effect. So what she found in her paper is using the t-test in the presence of time trends results in a conservative test decision under permuted block randomization, even for small time trends, and that could be improved if you use ANOVA model, including the block size. That is a very good strategy to deal with. Then medium block size already achieve a good reduction in the inflated worst case scenario. So then I would go away from what we considered up to now. We considered whole procedures. So the whole sequences of a procedure was evaluated up to now. But when you communicate to a physician, he sometimes, I mean, what is the main argument against complete randomization? It's not balancing. Yeah, balancing is, I mean, that is stupid stuff based on biostatistician who tells a physician, okay, you are more powerful if you have balancing. And that forces that some physicians do a clinical trial and found 84 patients in one group and 87 in the other group. And then he comes 2 weeks later to you and says, oh, okay, I have randomized an additional patient to the group where I need another one to be balanced. Stupid stuff. I mean, you have no loss in power in that case. But anyway, I mean, what is the problem with complete randomization? The complete randomization has the problem that everybody is afraid of a particular sequence. So getting only treatment A. And we all know that if you have 200 patients in a clinical trial, the probability to get this sequence is very low. So that brings me to the end that I want to study some special sequences. And that is a point where I have some relation to Linda. And well, the first sequence which is very prominent is alternating sequence. The second is the, you call that on at one time. It's that one here. And this is the student allocation, which also can be reversed to put 0, 1, 1, 0 here and combine that. So this allocation sequence prevents extremely good against time trend. It balances it out, so I have no time trend. So our first non-centrality parameter will be 0, but the second has some effect. I calculated for all these sequences the non-centrality parameter for the doubly non-central t-distribution in that cases under selection bias and time trend. And then I make some specific assumptions to my evaluation because I think, okay, I have to fix something. And I choose NA equal NB equals 6. So I have only one transparency with n equal 8. Okay, but it's small enough. Okay, and then I choose the eta to be the treatment effect you can detect by a sample size of 12, and I take a quarter of that, so a very small effect. And I take the time trend effect in the magnitude of sigma. I mean, you can do everything what you want to impute in this formula, but I have to fix something to come to these p values here. And you see, interestingly, in some cases, the p-value is elevated above the 5% level, here in that case, here in that case. In some cases, you have no effect, and in some cases, you have a very conservative test decision. So you cannot detect anything with these things. And I think that is a nice argumentation to a clinician, because if I tell him, okay, you have chosen, unfortunately, you have a situation or a design of your clinical trial where you never have the chance to get a significant result, he must be very afraid of doing that one. Okay. Well, my recommendation is that similar things can be done for every randomization sequence, and I combine the tau e by putting together on an additive scale the time trend and the selection bias effect. And this is a formula. If you have q equal to 1.5, you have the sine function, which is mostly based on the previous assignment to treatment A and to treatment B, and here is the eta. And you can weight these parts for your own. And in the first version of the transparency, I have a WI in that, but it's not necessary, because you can relax or you can modify lambda and eta as you want to weight these factors as you might think that it is reasonable. And you can impute different shapes for the time trend in that, and probably you can also use a different version of the selection bias with this random selection bias effect, which is based for different populations, or you can use Miriam's formula for q equal to 2/3 or something like that. You can do that, and you can also use a multiplicative scale, and then do the evaluation again with the corresponding results which are presented to you. So you just have to recalculate the non-centrality parameter of the doubly non-central t-distribution. I did that. Okay. slightly seen. I'm sorry about that. It's well, the points here. The points are the values of the p-value for the doubly non-central t-distribution, and the lightness of the points are connected to the probability for a particular sequence to be in the randomization procedure. Here we consider random allocation rule for n equal 12. We have this eta as before and the lambda as before, and you see this picture here. And if you want to assess that, you have to notice that the wish, the thing you want to have is a procedure which is just in this area here. And you see, well, random allocation rule is affected by selection bias because you have most of the points going far away from the 0.05 level, and is affected by linear time trend as well, as you have points in that area, and there's a small number of points in that area here. I also calculated quantiles of the distribution of these points and the maximum and minimum value. And if you keep in mind that the 5% level is kept by the median for a linear time trend, and it is maintained, and is maintained in the 5% quantile for the randomization, for the random allocation rule, and no wonder, big stick. Big stick lies a little bit more with the points here in that area. It's more condensed in this form here, and you see that it widely prevents against selection bias when you consider the p-value of the test distribution with this under these assumptions, and it widely presents 75% quantile of the distribution against linear time trend. Well, and my recommendation would be that persons who did this can draw pictures like this. They are more blue under the screen. I'm sorry about that. I would, in future presentations, I will skip to the LaTeX versions like Rosemary do. Okay, but here you can see that the difference of the two procedures is different, and you can communicate and give some scientific arguments what you want to have in your clinical trial and what it should be made. So the main question is, how do I come to eta and how do I come to lambda? Well, as I said, if you think about surgical trials, there should be a lot of data available. I mean, if you think about randomized clinical trials where you have a sham surgery done, and you see and you compare the surgical improvement over the time, so there could be some experience about that. And well, information about eta is a little bit hard to do, but Bill has done with Lieven together the paper in the biometrics, where they are where it is possible to extract from a clinical trial and parallel group trial the selection bias effect from the data, so it could be estimated. And we need some time to fix it more and not to do it by what is in your mind, so coming up from the sky. So I presented the framework for a scientific evaluation of randomization procedure and bias, which is possible and could be included in the so-called TSAP. TSAP stands for Trial Statistical Analysis Protocol. So it's one important document which should be given additional to the protocol of the trial, and where you specify your statistical settings. So that could be one place to impute that. well, it is easy to implement other randomization procedure with this framework. And we also are looking for dichotomous endpoints and survival endpoints, and there's a work on of a PhD master student in my department. She is looking to a formulation of the selection biasing policy on the randomization procedure. But you even can do that by simulation. You will not get a nice formula which I presented to you. And one caveat. I'm sorry, I'm used the wrong test. That's not what I want to do. But it is that what the physicians do. And they know the t-test. I would recommend to use a randomization test and do the same evaluation. But showing them the results of a randomization test, I have much more communication. But showing them you do the wrong thing after randomization, and that happens, brings some awareness of the problems to their mind, and not doing randomization and then forget about all what you do in the analysis phase of the trial. And then I would like to recommend our randomizer R package, which is coming soon. Please take a note on our website. So, not 50.
And I think that randomizer is going to do the randomization plus also provide the randomization test.
Yes, second phase.
Just to advertise what you're doing even better.
Yeah, thank you very much.
Thank you.
Okay, thank you very much. So here are some references.
Must be educated. I never heard of a doubly non-central T distribution until I have to go and look it up. Just a comment about bias, time bias. Actually, we expect it quite a lot in trials, but we don't call it bias.
Yeah.
Because actually, when you start a trial, the CI open up his centres first, then all the teaching hospitals get on board. So they've got more per protocol patients, the more sick patients, the better running centres. And then general hospitals start coming in later along the line. And in fact, one of the arguments I get from clinical colleagues about not doing adaptive designs is they want to have heterogeneity.
Mm-hmm.
They want to see across different settings.
Yeah.
But what happens is that the effect, we do expect to see the effect fall over time, because the worse quality centres start coming in later in. So it's like a time effect as well, but it's not bias.
Yeah.
So a clinician will say, well, that's actually what is more like the truth.
Yeah.
And if you just have the specialist teaching hospitals, they'll be overstating the effect. The other ones, you get smaller effect, and then obviously the middle is the truth about what you expect to see. So that's another example of longitudinally. You expect to see the treatment effect falling over time, but then that's just actually, you could say, regressing to what the truth is, not bias at all.
Yeah, thanks for this comment, Stephen. Well, we have the same discussion in the review of Miriam's paper. Well, I'm aware that the term bias is not really correct in that sense, but yeah.
I mean, it has been called chronological bias in the
literature.
randomization.
Yeah, yeah.
But whether it's actually bias in your sense is a different issue.
So thank you very much.
Thank you very much.